In this section, we talk about the pen string situation. Okay, we consider a very long structure, or a straight bar, actually a straight bar. Okay, and at the two ends of this straight bar, they are fixed. The ends are fixed. Okay, fixed end, and the coordinate x, y, z are arranged like this. Okay, so along the straight bar, it is the z-axis. Okay, and the cross section of the straight bar, the cross sections of the straight bars are located in the xy plane. Okay, we want to mention the point that even though we have a straight bar, if the loading is not very special, then the problem still cannot be reduced to a two-dimensional problem. So we have a very special shape of the bar, but we still need some special loading instead that in order to get a simple problem. Understand? So if the loading is very complicated, then the straight bar is still in a three-dimensional situation. Now, if we want to have a two-dimensional situation, the loading must be simple too. We look at the constitution here. The external loading distributed uniformly along the z direction means that in every cross section, the loadings are the same. Okay, this cross section, this cross section, this cross section, the loadings are just the same. And also, the second condition is these loadings must be applied in the xy direction. Okay, they should be pointed in the xy direction. This is the second condition. The third condition is the bar must be fixed, must be in a fixed end situation. The fourth condition is it is a straight bar. Okay, and the fifth condition is that the size and the shape of every cross section are the same. What do you mean? Means that along this straight bar, if you cut a cross section out, you find a shape in size and shape. If you cut another cross section, you find the same size and same shape. Okay, so in one word, this straight bar is in a uniform situation. Okay, now I want to emphasize that the fixed end conditions can be replaced by this. If the bar is not finite length, it is in a infinite length. If it is a bar of infinitely length, then the ends of the bar must be fixed too, because it is infinitely long. So since it is infinitely long, the two ends cannot be moved. Okay, because in the infinity points, nothing can be moved. Okay, so this condition for a finite straight bar can be replaced by this condition, that the bar must be infinitely long. Okay, let us look at some practical example, like the retaining wall. See, there is some soil, okay, at this side, which is retained behind the wall. Okay, see, this is a typical cross section of the retaining wall. Okay. This is one practical example. Another practical example is this. For example, we bury an underground channel under the ground. So above the channel, there is some soil pressure. Okay, and every cross section of the channel is the same. Okay, this is the second example. The third example is underground water pipe with water pressure inside. See this water pipe buried under the ground, okay, and then so outside the pipe there is some soil pressure uniformly distributed along the pipe, and also inside the pipe, some water pressure distributed uniformly along the z-axis. Okay. Now let us look at the displacement field of this special structure. We put the straight bar in the horizontal direction. See here, this is x, y, and z. Okay, this is a straight bar, and we put it like this. Okay, we place it like this. So the z-axis now one from the left to the right. Okay. Now I want to argue that the displacement in the z direction must be equal to 0. We have some displacement UVW, okay, but the W component must be 0. This is the displacement in the z direction. Okay, the displacement in the z direction must be equal to 0. Why? Because every section of the straight bar is the same, and also the loading along the straight bar in the z direction is uniform. Okay, so if we look at the middle plane here, we have the symmetry. The right hand side and the left hand side are just the same. So the displacement in the z direction cannot go to the right, and it cannot go to the left too, because if you go to the right, then the symmetry will be broken. If you go to the left, then the symmetry will be broken. Okay, no symmetry at all. So in order to reserve the symmetry, to keep the symmetry, the displacement in the z direction cannot be go to the right, and also cannot be go to the left. So the final result is it must be 0. Okay, so the displacement in the z direction must be 0. No displacement in the z direction. Okay, so we know that at the end point W equals 0, at the middle plane W equals 0, at the right end W equals 0. Now we cut this half bar to here as the free body diagram. We cut this free body diagram here. This is the middle plane. Okay, this is the middle plane. Okay, this is the right end. Okay, right end. Now we can repeat the same argument. See, for this free body, every section is the shape of and the size of every section is the same, and also the loadings are uniformly distributed along the z-axis. So this free body must be in a symmetric situation too. So by such kind of argument, we understand that the middle plane of this free body must have a 0 W value here. Means that the displacement of this middle plane cannot go to the right and also cannot go to the left. Okay, so W equals 0 in this cross section. See, in this procedure, we understand that we can have a lot of cross section W equals 0. Why? See, in the very beginning, we understand that W equals 0, W equals 0 here, and then we argue that W equals 0 here. And then we cut the cross section here, okay, to argue that the W value equals 0. And also, W value equals 0 here too. And also, we can keep cutting the free body to say that, oh, the W value equals 0 here. The W value equals 0 here. So, finally, every cross section, we can have the same result. W equals 0. Okay? this is a very useful simplification for the mathematical problem. Okay, W equals 0. And U and V not depend on Z. Why? Because the loading is uniform along the Z-axis. And also the shape and size of the bar is uniform along the Z-axis. So the displacement cannot be changed along the Z-axis. Okay? See, if you change, then the symmetry will be broken. Okay? So means that every cross-section, the displacements are the same. If the UV displacement in this cross-section is different from the UV displacement in this cross-section, then the symmetry will be broken. Okay? Which is not allowed. So every cross-section, the displacement U and V are the same. So as a result, U and V are not depend on the Z coordinate. Now let us compute the strain component. Epsilon ZZ equals 0. Why? Because W equals 0 here. Okay? Epsilon XZ equals 0 because W equals 0 here. And partial U partial Z equals 0 because U does not depend on Z. So partial U partial Z equals 0. So we have epsilon XZ equals 0. In the same deal, we have epsilon YZ equals 0 because epsilon equals 0 here. And partial V partial Z equals 0. So we have these 0 components. Let us write it down to the string matrix, okay, like this. So we have all the way, a lot of 0 components, at the edges of the matrix, okay. And also the components inside this matrix cannot depend on the coordinate Z. Now we look at the stress component. Stress component for, in the plane stress situation. See, first. We deal with the shear stress. See, we have shear strain here equals 0. Epsilon XZ, epsilon YZ are 0. Epsilon XZ, epsilon YZ are equal 0. So sigma XZ and sigma YZ are equal 0 because the shear stress and shear strain relation is very simple. So from the 0 shear component, we can have the 0 shear stress component. Okay. Now, how about the normal stress component? We look at this relation. Epsilon ZZ equal to 1 over E and then time this formula. Now, epsilon ZZ equals 0. As we have mentioned before, epsilon ZZ equals 0. So we have a mathematical formula to relate all these stress components. Now we solve sigma ZZ out here and then find out that sigma ZZ equal to nu times sigma x plus sigma yy, which means that sigma ZZ not equal 0. Okay, we summarize our relation in this matrix. Sigma xz equals 0, sigma yz equals 0, sigma zx equals 0, sigma zy equals 0, but sigma zz not equal 0. Okay? So let us do some comparison. The string component, the string matrices in the plane strain situation is like this. While the stress matrices is look like this, we have all the CO component here, but for the string matrices, but for the stress matrices, only a part of the components at the edges are zeros, but this one sigma zz not equal 0. Okay, this one and this one are not in the same situation. Let us summarize our situation here. The stress matrices will be written like this, and the strain matrices will be written like this. In fact, it looks like a 3 by 3 matrix, but in fact it is a 2 by 2 matrix, right? It is a 3 by 3 matrix, but in fact it is 2 by 2 matrices. So we want to relate this small matrix and this small matrix like this to get a 2-dimensional stress-strain relation. Okay, we don't worry about this one. Why? Because if we relate this one, this small one to this small one, we can solve problem. And once we can solve the problem, we can get the sigma x and sigma yy, and then we put into here to get sigma zc. So sigma zc can be obtained finally. Okay, so now we concentrate at this part. Let us first look at the 3-dimensional stress-strain relation. We have such kind of relation. But how about E? E is epsilon xx plus epsilon yy plus epsilon zc, right? But now epsilon zc equals 0. So only epsilon x and plus epsilon yy remain. But this one equal to E star. Okay? So we can change from little e to little e star. So this little e will be replaced by little e star. Okay? So we write it like here. We write this relation, put it like here. Okay? And in the same deal, we can put this relation to here. Okay? And in the same deal, this relation, put it to here. Okay? We don't need this. We don't need this one. We don't need this one. See, I make some mistake. This is not equal 0. This one equals 0. So we don't need these two relations. This one and this one are equal 0. This one equals 0 and this one equals 0. But this one not equal 0. Okay, we erase this. This one not equal 0. So we put this right here. Okay. Now finally we construct a set of 3 equations for the 2-dimensional case for the plane string situation. Understand? Originally, for a 3-dimensional stress-strain relation, we have 6 equations. 1, 2, 3, 4, 5, 6. Now we take only 3. 1, 2, 3. 1, 2, 3 here. Not 0. Okay? Now, see, there is no sigma xx. We have only xy component here, right? We can use this to solve problem. After we have solved the problem, we get sigma xx and sigma yy and put it here to compute sigma zc. Okay? Let us summarize the whole situation. For a 3-dimensional stress-strain relation, we have 1, 2, 3, 4, 5, 6 equations. Okay, E like this, F, lambda like this. For the plane stress situation, we have 1, 2, 3 equations. Okay. For the plane strain relation, plane strain condition, we have 1, 2, 3 equations. And the outlook of the normal stress look very similar. Like this, and like this. We replace little e by little e star, constant lambda by constant lambda star. Here, the same, doesn't move, doesn't need to be replaced by lambda star. Lambda, lambda star, lambda. E star, E star. Okay, so the normal stress component can be computed from the normal strain in a similar relation. Okay, and for the shear relation, they just look the same. This is the whole picture for the stress-strain relation for 3-dimensional problems and 2-dimensional problems.